Good morning, everyone. Today we continue the topic of probability theory. And in the last lecture, we review major concepts in conditional probability, as we can see now on the slide. And also, we introduced a few concepts how to like create Monte Carlo simulation to simulate some uncertainties and to evaluate the outcomes of the uncertainties, and then we can compare between the analytical solution and the simulation results to see how much they are comparable. Of course, in the last lecture, we introduced the concepts for some simple applications. However, as we mentioned last week, that there are some very complicated problems to be solved analytically. So the simulation will be always available in such situations, and we will see during this course, inshallah ta'ala. Um, so now now it seems that I opened the PDF, not the PowerPoint, but it is not a problem. So we can here also we talk a little bit about Bayes theorem or Bayesian theorem, and we showed that it is very important in estimation theory, in also in machine learning, in many different applications. There's one example that I asked you that you review it, and but I will also give some more examples. Let us take this example today to see how to apply this concept of conditional probability. So in this example, it says that it has been estimated in certain country that 10% of the population are very obese. So it means that they have high level of overweight. It has been estimated that 70% of those obese suffering from high blood pressure. However, only 10% of non-obese people have this disease. So there are some people that 70% who are already like overweight, they have high blood pressure, and only 10% of those who don't have overweight, they have this high pressure disease. So the question here that if you select one person randomly from the country or from the society, find the probability that this person she has high pressure regardless of her weight. And if we found that she has high pressure, what is the probability that she has overweight? Okay, so now we can see this is one application that we can apply Bayes theorem in order to get like more accurate results about the situation, because there's a conditions here. There's we have conditioned events. The first condition that the condition between being overweight and have high pressure. So sometimes these analysis or this statistical analysis might lead to some kind of like misleading results, because some people they consider only one event and they don't consider other events. So if you look to the history up to date, actually, in health system, for example, you can find a lot of contradicting like results. For example, in 90s, they were mentioned about coffee, that it is very harmful for body, and they mentioned that the coffee, or like drinking a lot of coffee, not even a lot. I read myself that they say if you drink more than 3 cups of coffee per day, then you will get health problems in your heart and blah blah, many different problems. This was in 90s. Nowadays, you can find completely reverse results. You can say that, or you can see a lot of studies recommend coffee, and they say that coffee it has antioxidant high component, and it is very healthy. Of course, for some people, they have some problems like ulcer problem or something like that. It might not be very good for them. But in general, nowadays they recommend coffee. Okay, and why this like contradicting in the in the conclusion about the coffee. And also you can see the same about the animal fat. So animal fat in 40s and 50s and 60s, it was considered as like the most harmful like food for a human. Nowadays they recommend it, of course with some levels, but they recommend it. So they recommend animal fat to be eaten, to be added to our food, because they said that it has many benefits for our body. So why this contradicting or contradiction in these results? Actually because of the such kind of conditional probabilities. They made some kind of like statistical analysis, because these recommendations are based on statistical analysis. They take, for example, 1,000 person, they made analysis, they found those, they divide them into two parts, for example, randomly, and then they study for those who have high pressure, or for those who have heart problems or heart diseases, and then they look to their food. Do they eat a lot of fat, for example? Then okay, those people eat a lot of fat, then they say that the fat is related to this, and this is not correct every time, because you need to look to other conditions. They might have some other kind of living style that it affect this one. So okay, let us return back to this example. So now when you see such kind of examples that you want to solve, the first thing that you must do is to define the events. Define the events as they are given in the problem or in the example. Sorry. So now, if you look to this example, so you can see that they say in certain country 10% of population are overweight. 10%. Okay. So what that mean? The first thing that you need to define this overweight. So here I define the overweight as O letter. So I call the event O equal to that the person has overweight or is obese. Okay. And then the second thing is the high pressure. So now I defined high pressure. The person has high pressure as letter H, as you can see. Okay. So now I have only these two, like overweight and high pressure. Of course, the OC means that the complement of being overweight. The complement. What is the meaning of the complement of overweight? Means that the person doesn't have overweight. Simply like that. So OC is the complement of O, and it means that he or she non-obese or not doesn't have overweight problem. Okay. Now and then I look back to the example and I try to define those probabilities. For example, what is the probability for a person selected randomly from this country to be overweighted? So this probability is given. As you can see, it is 10%. Okay. So simply it will be 10%. So it is 0.1. Okay. What is the probability of a person to have high pressure conditioned, or it is given that this person has overweight? It is given here. So it has estimated that 70% of those who have overweight or obese suffering from high blood pressure. So it means that it will be 0.7. So the probability of being of having high pressure given that this person has overweight is equal to 0.7. Okay. Then they said in the example, however, only 10% of non-obese people have this disease. So only 10% of those who doesn't or who don't have overweight have this high pressure. Okay. So it means that the probability of high pressure, given that the person is like in good shape or doesn't have overweight, is equal to 0.1 as it is given in the example. Okay. What are the requirements of this example? The first requirement is find the probability that this person who have been selected or has been selected randomly has high pressure, regardless of her weight. So regardless even whether she has overweight or not. So what is the probability that this woman has overweight? So the probability of H, we use the law of total probability as we explained before. So the probability of H equal to the probability of H given O times probability of O plus probability of H given O complement times probability of O complement. And this law, actually we use this one, as you can see it here, the law of total probability. It was given this this one, yes. So probability, this is a general way. So if we have BI events that all of them, they are mutually exclusive, and then the probability of A equal to the summation of probability of A given BI times probability of BI. Now we have O complement and we have O. O and O complement, actually they are mutually exclusive because one is having overweight and the other doesn't have overweight. So they are already naturally mutually exclusive. So in this case, okay, let me change to the PowerPoint. It is easier to move than this one. So I just stop. Okay, unfortunately, I couldn't find it, so let us go back to that. Okay, so we can also here. Okay, so this is uh, the law that we used in solving this example. So now we can see here that the probability of H equal to probability of H, as we said, that given O times probability of O and plus probability of H given O complement times probability of O complement, and that, now we just substitute. So probability of having high pressure given overweight is given in the example as 0.7 times probability of being overweight is 0.1 plus probability of having high pressure given that no overweight is 0.1 times probability of don't of not having overweight is will be 1 minus 0.1 because the probability of being overweight is 0.1. So the rest of the people, 90% of the people, will not have overweight. So in this case, it will be multiplied by 0.9 and the result will be 0.16. So 16% that this woman will have overweight. So this is in general the probability. In other words, this it means that out of 100 tested persons, we will have 16 out of them with overweight. The second requirement in the example is that if she has overweight, if when we test the pressure of this person, she has overweight, what is the probability that she has overweight or she is obese? So now we apply the reverse. As you can see, this here we have the probability of O given H. We have already probability of H given O. Now we are looking for probability of O given H. And now it is very straightforward that we can apply Bayesian theorem here as it was given. And then we apply it. So it gives us that it is 44% that this person will have overweight. Okay, only 44%. Okay, so now we have I may go to another example. Here you can see that there's one code to simulate this problem. So it is exactly the same as we did in the last lecture. So we define first certain probability, and here you can see that I assume that the number of population is 1 million in this country, n equal to 1 million. Then I generate this O that they are 10% to be overweight, and for those who have overweight it will be -1. For those who are normal weight will have 1. Then I define the high pressure, and the high pressure in the beginning I start to generate all zeros row with the same size of O, okay, because same size of people. You can of course put here n and 1, or you can use size O. Then I count how many person they don't have overweight, because as I said, when we say that 10%, it is a probability. So what is the meaning of probability? It means that one out of 1 million, not necessarily that you will find exactly 100,000 for the 10%, or 900,000 for the 90%. It is on the average, so it is just probability. Okay, so here I count the number those who have non-fat people, and then I define here the people that find those who have like in the beginning they are non-overweight, and in the same time they have pressure. So in this case, by this way we can define these probabilities, and I recommend that you try to study this code carefully, because I explained the concepts actually of how to make these codes last lecture, but try again to study this code. It is very small code, as you can see, and it is easy to understand. And when I run this code, I got this probability 0.16 or 12 and 0.436, and if you compare it with the previous result that we got, so it was 0.16 and 0.44. So it means that the simulation is very close to the analytical results. The same example, I did it, but with the conventional way, because many people that it is not recommended, by the way, to use for loops in MATLAB or in Octave. For loops will make the code very lengthy and non-optimized, and it will be very time consuming. So it is not recommended at all to use for loop in your MATLAB or in your Octave codes. In general, in codes, it is not recommended to use for loop, except some high-level languages like Julia, for example. In Julia, you can write the code in the way that you want, because when you make the interpretation of the code, the interpreter will convert it to the most optimum way internally. So you don't have to take care about how to generate your code or optimize your code, because the optimization will be done automatically in the in Julia code. I have no idea about Python if they use also the same way. But here in MATLAB, what I did, I generate the same code but using for loop, as you can see, for int, and so on. So to generate this code, the time required to get the result, it was 600 times more than the time required by using this code. Even it is the same to solve the same problem. But here I avoided to use for loops, and here I used it in using the basic way to generate it with the for loop. So try also to update your skills when you write codes, especially that if you are in the future, when you start doing your master thesis or your PhD thesis, in many situations you will have a lot of parameters. For example, if you want to simulate the propagation of electromagnetic waves out of antennas to some area, and you want to take steps by 1 meter, and you want to cover like certain region, so sometimes you need like millions or hundreds of millions of cases and calculations. If you want to do it with using this simple way of for and next loop or for loops, sometimes it can take like months in order to get a result. And this was happened also with some of our colleagues that can take like 1 week. They run the code over their computer for 1 week. After they change it with this using the facilities of vectors and matrices multiplication available in MATLAB, the time reduced from 1 week up to only 1 hour to get the result. So always try to use the features of the code. Every code or every programming language, it has some internal features. So try to always to use the internal features available. So in Octave and MATLAB, the internal feature is the vector manipulations and matrix manipulations. So always try to use this. Avoid using for loop unless it is necessary. Sometimes it is me myself, I need to use for loops in some cases because there is no other option. But when there is other option, always try to use the available features of the programming code. I also explain another example, this one about quality control. So there is one quality control test, for example, in mobile phone. Let's say in some company, vendors or manufacturer of mobile phone, let's say Nokia, for example. And you know that after the line of production, at the end of the line, there is the quality control. If you buy anything like equipment or whatever, so you can find in the front of it in the box that like QC, quality control passed. So this quality control, they check the product, the gadget, they check it if it has any like defection. So like for example, software or hardware or crack or something. So now the quality control test, they say that it is 95% effective in detecting damaged mobile phone. So if the mobile phone has a damage, so this quality control performance, it will be 95%. It will detect that mobile phone. Okay, what it means? It means that on the average, only 5 detected or defected phones will go through the quality control. From out of 100, only 5 will pass, but 95 will be catched. 95 will be detected. Okay, but there is no like ideal quality control test. So they say here that this quality control, it gives you false positive. What is the meaning of false positive? It means that the mobile phone doesn't have any problem, but still the red light will be alarming that this mobile has defect. So what you will do, you will take off this mobile from the line production for further checking. So this will consume time. This will reduce the production. So this is the false positive result for only 1%. So only 1% of the mobile phones which are good, that it will give us like wrong alarm that it has defect. It is known that 0.5% of the total mobile phones from this company, it has some kind of damage. So according to the history, looking to the history, they found that 0.5% or 5 per 1,000 mobile that go to the market, 5 of them will return because they have damage. Okay, so this is statistical information. Now, for a test of certain mobile phone, the quality control test was positive. So there's one mobile now. It was alarming that this mobile has damage. What is the probability that this mobile is really damaged? What is the probability that this mobile, it has really some kind of damage? Again, as I said in the beginning, so also in the exam, in your research, in the quiz, when you have such kind of problem, the first thing, define the events. What the events that you have? The first event that I have, that the tested mobile is damaged or not damaged. Okay, so now we define K. As you can see, K here means that the tested mobile is damaged. Okay, and the other event, of course, K complement will be that the tested mobile is not damaged. Okay, and the second event I define is C. C means that the positive test is obtained. Okay, so we got positive test or we got alarm that this of damaging or of detecting of of damaged mobile. Of course, this alarm, as I said, it can be due to like defected mobile, or it can due to false positive. Okay, what is the requirement now? The requirement in this example, as you can see, what is the probability that this mobile is really damaged? So it means that I am looking for finding the probability of the mobile is really damaged is K, given that we received positive alarm. We received positive alarm. Okay, so this equal to probability of K and C divided by probability of C. We know this from the conditional probability. And then I can use Bayesian theorem. So it is probability of C given K, because here we have probability of K given C. I can like swap them. Probability of C, probability that we got positive alarm, given that the mobile is really damaged, times the probability that it is really damaged, divided by the probability of receiving positive alarm. The probability that you receive positive alarm, it is the law of total probability again, equal to the probability that you receive positive alarm given the mobile is damaged times the probability that mobile is damaged. It is like the above, you can see, plus probability that you receive positive alarm given that the mobile is not damaged times probability that the mobile is not damaged. Now, if you look to this formula and let us collect the numbers from the example, the probability that you receive positive alarm given that the mobile is damaged is given by 95%. Okay, it is the efficiency of the quality control in detecting damaged mobile. Okay, so this will be 95%, so it is 0.95. What is the probability that you have damaged mobile? As it is given here, 0.5%, because from statistical analysis, 0.5% of all mobiles, they have some problems. So now we multiply this by 0.005 divided by the first term is exactly the same as the above term, so it will be the same, plus now the second term here. What is the probability that you receive positive alarm given the mobile is good? It is given here. It is 1%. It is false positive. It is 1%, so it is 0.01. What is the probability that the mobile is good? It is 1 minus 0.005, because probability of being bad mobile or has some defect is 0.5%. So the probability of being good mobile will be 1 minus 0.5%. So it will be 0.995, as you can see here. Substituting these values, you will get 0.323. What that mean? It means that only 30% of this detection, okay, only 30% that the mobile has real damage. Okay, so in that sense, this quality control is actually quite ineffective. Okay, or even you can see that it is bad quality control here, because only 32% of the mobile will be defected and the others is not. Why we got such result, such strange result? Even the effectiveness of this quality control is 95%, but why we got this low like performance in reality? Okay, let us now dig down in this example to understand what is going on here. To understand here, assume that this production line will produce in one day 1,000 mobile. Okay, they will produce 1,000 mobile per day. I picked up this number just for like to demonstrate like some important aspects here. Okay, so this company produce 1,000 mobile per day. Okay. Now, in this 1,000 mobile, you look here to the example, it is only 0.5% of the total mobile will have some kind of damage. What that means? Out of 1,000 mobile, we would have 5 mobiles on average, can be 4, can be 3, can be 6, can be 7, but on average, there will be 5 mobiles will have some kind of damage. Okay, 5 out of what? Of 1,000. Okay, great. For the false mobile, they said that 1% of the good mobile phone will give us alarm. Okay, so 1,000, 1% of 1,000, it means that 10 mobiles, 10 good mobiles will give alarm by this quality control. Okay, so the total number of the mobiles which will give alarm, it will be 10 plus 5. So it will be 15 mobile on average. Okay, out of 15 mobile, how many mobile that they have really damaged? Only 5. So 5 divided by 15, this gives you this closer to 0.323. Okay, so this gives us the real reason why we got this low percentage. If I ask question that how we can improve this quality control, how we can improve this quality control, actually the best way to reduce this quality control is by reducing this 1%. So the false alarm is the major reason for this bad performance in this quality control. Okay, so this is very important. So now, and you can actually check it yourself. So after the lecture, come to this equation and try, for example, to put that it is effective 100%, not 5, not 95, even 100% effective in detecting damaged mobile phone, and keep this 1% or 2%, and then check the result and see how this result will be changed. And then you can keep this 95 and then reduce the false positive to 0.1% and check how this will affect the result. So now you as like maybe like line production engineer or quality control engineer, by using this simple example, you can see where is the problem in the quality control, and then you can try to improve your quality control tests in order to have more efficient way to deal or to detect the errors. So now this is actually not only for this example of detecting mobile damaged mobile. The same example you can find in detecting diseases in certain hospital. The same example you can find in detecting like symbols in digital communication. How to detect what is the probability of detecting certain right symbol, given that you receive that symbol, for example, or that received signal in digital communication. This example can be applied in different ways, and also you can see it, for example, in quizzes, you can find it in exams, you can find it later in your research activity. You can, if you are working either in telecommunication or computer science or in power system, this example, even it is quite simple, in the same time, it is very, very important in understanding what is going on in like conditioned case. In machine learning, for example, I because I'm also teaching machine learning here in Finland, so there's one chapter about like Bayesian algorithms for statistical inference is called. Or in machine learning, a lot of applications using this Bayesian, simple Bayesian, but of course with different application, because here we have only one condition, but now we can have like 100 of parameters as a condition. Okay. These are the exercises here was given, but it is not required from you to return the result, just for you that you can use. And another example given here. Okay. Okay. After this part, now we study so far the concept of probability. We gave the axioms of probability theory, the three main axioms, and also some theorems based on those axioms, and then we define different kind of probability, that logical based or set theory based probability analysis, and then the long run based probability. And after that, we jump to one of the most important topics in the probabilities, the conditioned or conditional probability, and it is extension of Bayesian theorem. And now we have seen several or at least two examples about the application of conditional probability and Bayesian theorem. Um, After this part, which was actually one of the pillars in random theory, we come now to the second very important topic, is the random variables. Um, what are random variables mean? Actually, random variable is nothing but mapping. What I mean, before I let me go to the whiteboard so we can explain a few things here. Okay, it's better on the whiteboard that just a minute. Okay. Okay, so now you can see the whiteboard. If you think, let us take the example of throwing or flipping two coins. So out of that experiment, we will have this sample space, like a head tail, tail head, and tail tail, for example. Okay, this will be the sample space of throwing two coins, or throwing or flipping one coin two times. Okay. Now when we talk about a random variable, the random variable is the concept that gives us the capability to use numbers instead of events. Okay. Um, for example, um, what is the probability of the cosine of head equal to 1? Doesn't have any meaning now. How can I take the cosine for certain event? It doesn't have meaning. Okay. Or I ask you, what is the probability that head plus head tail, this data equal to 3? It is meaningless, because now we are dealing with some descriptive events. Actually, even the dice which has point, 2 points, 3 points, and up to 6 points, actually, even in this case, they are events. I mean, the outcome of throwing like a dice will be the face of one dot. You should write it in this way. Face, for example, face of one dot. Face of two dots, and so on. So they are events. They are events. Dealing with events is not straightforward, or is not convenient to use in mathematics. Okay, so what we need to transfer or to map these events into numbers. So the idea that we have here, we can say that this is the event space. We need to convert this. Yeah. To convert this just a minute. It seems that has let me close. Okay. Okay. So now we have here the event space, okay, and then we convert this event space into real numbers. Okay, this process of mapping, is called random variable. Random variable. Actually, the name of variables can be sometimes misleading. It is not a variable. It is a mapping process. It is a mapping process. Convert from event space into real numbers. So event space, instead of saying head, tail, and so on, then we have here real numbers. This will be more convenient to deal in mathematics, especially, for example, when we deal this in like in time series signal, in like in wireless communication, we deal with signals, for example. So it all the time, this signal, the amplitude of the signal can be itself, it can be a random variable. Okay, so this gives us a lot of facilities that we can use. Now, if I just erase this one. Okay, so let us define that the random variable, you can, by the way, define the random variable in different way, as we will see. So if you define the random variable as the number of heads, so we have the now the outcome of the experiment is the sample space. As we said, it is head, head, tail, and tail, head, and tail, tail. Okay. So we can define the sample space or the random variable. Maybe x is equal to number of heads up there. Okay. So now x equal to what? X equal to, in the first case, we have two heads. So we have two, or head tail, we have one, or tail head, it is the same one. So we don't need to repeat one. And then tail is 0. So now this random variable x, it has three numbers, 2, 1, 0. It can be one of the three numbers. What is the probability that x equal to 0? X equal to 0 at tail. And if the problem or if the experiment is equally likely and everyone will be 1/4, so the probability that x equal to 0 is equal to 1 divided by 4. What is the probability that x equal to 1? Probability x equal to 1, it can happen two times, at tail head and head tail. And these two, everyone is 1/4 and 1/4, so the total is 1/2. And finally, the probability that x equal to 2 is equal to, at one case only, head, and this will be also 1/4. Okay, so the summation here must be 1. The summation must be 1. So the summation of x equal to 0 plus x equal to 1 plus probability of x equal to 2, the total must be 1. If I asked you what is the probability that x equal to 3, of course equal to 0, because it is not possible that you will have 3 heads but out of experiment by throwing 2 coins or flipping 1 coin twice. Okay, what is the probability that x equal to -1? It is also 0. It is not possible to have minus head. Okay. The nice thing here, when we deal with such numbers, now we can define, for example, the probability mass function. So now we can draw things, x and the probability of x. So probability at x equal to 0, okay, is equal to 1/4, and x equal to 1 is equal to half, and at 2 equal to 1/4 again. Okay, so now we have this mass function of the probabilities. Now we can draw, but before, how could we draw? How could we put here that this is tail and this is head and tail, or tail and head? It is not possible. Of course, this one represents this evidence, but now we have numbers. So this is very important to remember always, that the random variable representing evidence from evidence space into the number to the real number, and those x can take from -infinity up to infinity, plus infinity. You can put any numbers. Okay, one of you might ask me question, can I put that tail or can I define x equal to sum of tails? Yes. So in this case, I have head, x equal to 0 for head, and head tail. In two cases, it will be like x equal to 1, but now it will be for the tail, not for the head. One might ask question, can I put, for example, x is equal to the number of head but square? Yes, you can. You can put, for example, in the first case, we have head, then x equal to 4, because 2 squared equal to 4. And the others, x equal to 1, and then x equal to 0. Just real number. So just you need to remember what real number that you use to express this event. So the connection between the events, okay, to the real numbers, this map should be remembered. So you know that this event used for this real number. So this real number represent that event 1 or event 2. Okay. However, remember that it is not function. It is mapping, not function. There's a difference between mapping and function. Okay, because here you might have the same number here representing two different events or two double of different events. Okay, yeah. So this is about the concepts of conversion. Another thing I can say now: what is the probability that cosine by x equal to 1? Okay, here cosine by x equal to 1, x can have like 2 or 1 or 0. Okay, so for the cosine, you know that for the cosine is usually start with 1 and then it goes like this. Okay, so cosine 0 equal to 1. So this implies that this equation implies that x equal to 0. So the probability that cosine by x equal to 1 is equal to 1 over 4 because this happened at x equal to 0. Okay, so now you can take cosine, you can take the square root, you can take tan function, you can perform any mathematical equation that you want to do with the random variable. So this facility was not possible without defining the random variables. Okay, let's stop sharing. So now you can see that this is the main concept of the mapping between the event space to the probability space. Here we give another example about this mapping. So now what we define that you throw or draw or toss a coin, okay, or flip a coin that it has the probability B of being head. Okay, it has probability B of being head. Okay, and in this experiment, you repeat flipping the coin until you got tail. When you got tail, you stop. Or the reverse, of course. Or you want to get a start, and when you get head, you stop. It depends on your definition. But the idea here that we define the random variable n is the number of flips required to obtain head. The number required to obtain head. Okay, and the probability of head is equal to b. Okay, let me here explain how this could be performed. Um, I think this one, it has also capability that I can write over the screen with this PDF, but I have not used it before, so I need to allocate. Where is it? Yes, pencil, yes, one. Yes. So now, if you, as I said, the probability that you get head is equal to B. This is the probability that you get head. Okay. Now, if you, the first flipping of your coin, you get head from the first time. So in this case, n equal to 1 because you stop now. What is the probability that n equal to 1? The probability that n equal to 1 is equal to B because now you got B. This is the probability B. Okay. But assume that the first flipping of the coin, you get tail. What is the probability that you get tail? Of course, it will be 1 minus B because we have only two outcomes. Okay. So what is the probability that n equal to 2. The probability that n equal to 2 means that the first time it was tail and the second time it was head. So it means, and they are independent. They are independent. So the first time I got tail times the second time I get head. So it will be 1 minus b times b. What is the probability that n equal to 3? The probability that n equal to 3, it means that I will do it here in details. So to understand what is going on, it means that, sorry, yeah, means that the probability that first time, first time, first time it was tail, and second time it was tail, and third time it was head. It was head. Okay. Now this is and. And means intersection. This is and. If you remember, when we talk about conditional probability, we approved that if the evidence they are independent, then the result of and will be the multiplication. So this will be the probability of that. The first is tail times probability second is tail times probability the third is head. And this will be the first is tail is 1 minus p times the second is tail is also 1 minus p times the third is tail is p. So it will be 1 minus p squared times p. Okay, so this is the probability that n equal to 3. And in general, that p, that n equal to n small is equal to p times 1 minus p of the power of n minus 1. Okay, so here you can prove that the summation of all probabilities must be 1. The summation of all probabilities of n equal to I, that must be 1. And the proof, I think it was already given in the, okay, let me now stop the pencil. Yes. So you can, okay, it was not given here, but you can prove it easily that you can take the summation of these numbers that to be n equal to I, from I equal to 0 up to or n equal to 1 up to infinity. You can easily prove that this result will be 1. It is just summation of of series. Uh, the previous example that we gave here, they are valid for discrete probabilities, but also it can be continuous. So in this case, for example, the temperature, the change of temperature is something continuous. So how could we define the probability of continuous thing? Okay, here it is hard to define the probability of continuous thing specifically at certain time or at certain value. And the result in this case will be 0, as we will explain after taking like short break. Okay, so to continue that, let us take a break, 10 minutes, and then if it is okay with you, of course, if it is okay that we can take 10 minutes, so you can just come with with them. They are different topics, as you can see, and it is good that to have little break so you can come with more motivation. Okay.
Okay, thank you.
Okay, inshallah, at 11:28 we continue, inshallah ta'ala. Okay, we'll come again. So we continue. Uh, uh, Before the break, we just introduced this concept of continuous random variables. So the random variable can be continuous. For example, if the random variable is the temperature, so the temperature can be like varying in continuous way, can be voltage, like the continuous voltage, can be, for example, force, or it can be distance. Okay, so it can be many things that can be represented as a continuous random variable. So when we deal with continuous random variable, we need to define different way to quantify the uncertainty in the random variable when it is continuous. It is not that easy that in the discrete case where we have discrete events. So in that case, it was easier to describe the probability of a discrete event. But when it is continuous, it is something else. Just let me take some example, simple example about voltage. For example, if you have like a random voltage, and this voltage from -2 volt up to 2 volt. If I just draw this here, maybe it is easier to go to the whiteboard, but let me do it here. Not this one. Comments, yes. Okay. And so we have random voltage, and this random voltage is in time, and this is the amplitude of V of t, and it is random from -2 volt up to 2 volt. So it is random in this way. The maximum is 2 volt, and the minimum is -2 volt. Okay. This random voltage, now it can take any value in the magnitude or the amplitude from -2 volt up to 2 volt. We want to quantify the uncertainty of this voltage. What is the probability that you got voltage equal to certain value? For example, the probability that V, let's say, equal to 1 volt. The probability for a specific value, this equal to 0. Why it is 0? Why the probability of voltage for any value, not necessarily 1 volt, for 0 volt, for 0.1, for 0.2, for 0.5, for -0.2, if you specify certain single element and continuous random variable, the result will be 0. The reason behind that from -2 volt up to 2 volt, actually we have infinity number of cases. We have infinity number of values from -2 volt up to 2 volt. For example, you say that 1 volt, okay, but also 1.0000001 volt, for example, is also there. So you can see here. So this value is also there. So 1 volt plus 10 of the power -20 volt is also there. Now, when you say what is the probability that V equal to 1 volt, actually, you mean that the probability that voltage equal to exactly 1, and after 1, you have infinity number of zeros. Exactly. It means that perfectly 1. And from -2 up to 2 volt, we have infinity number of levels. So in that case, if you take one level divided by infinity, the result will be 0. So you cannot specify a specific value in continuous case. But what you can do, you can define the voltage of some range or some period. So I can say, for example, what is the probability that V is greater than or equal to 1 volt and less than or equal to 1.1 volt. So this not necessarily be 0. This can be some value. Maybe it depends on the distribution of the voltage. Can be, for example, 0.2, for example, the probability, or 0.1, or whatever. So when you have range, then it is not necessary to have 0. Even very small range means that, for example, the probability that V greater than or equal to 1 and less than or equal to 1.00000001. This is not necessary to be 0. It might not be 0. But when you give just a specific value, single value, so the probability of any single value in continuous random variable is equal to 0. Okay, so in that case, we can deal. Uh, okay, so in that case, we can deal with the probability as the probability density function. We start to deal with density instead of dealing with a single value. So the probability of certain density, for example, from T here for the example of temperature, to be greater than or equal to T0 and less than or equal to T0 plus delta T, or for the voltage, it can be what the probability that the voltage to be greater than certain voltage V0 and less than or equal to certain voltage V0 plus delta V, for example. In this case, we can define certain probability. So this will be the probability small, okay, of the event of V at what? At V0 times delta V. So in this case, it is represented the area under this strip. So it is the area under this strip of the probability, under the curve. Based on this analysis, we can define what is known as a probability density function. A probability density function is the measure or the main tool to deal with continuous probability events or random variables. So the way to deal, how to find the probability of certain event, which is continuous event, we can do that by using the probability density function. The probability density function, actually, the probability density function is nothing but the histogram, or representing the histogram or the amplitude domain of the signal. Let me explain this a little bit to you. I go, yes, I will draw here. If we go to the same example of that I mentioned now, that we have time and we have voltage. Sometimes when I teach such courses for business school, so I need to use terms that they understand, like demand and the prices and so on. But when we deal here in electrical engineering, it is better to use the terms of electrical terms like voltage and current and so on. Okay, let me close this one. Now we have random voltage. So I need to have the pencil again. Organize this comment. Yes. Okay. Now we have just random voltage. This is the time domain of the signal. If you take the Fourier transform, we will get the signal in a frequency domain. Of course, I'm not going to discuss this today at least. We will come to the about spectral density when we talk about frequency domain. But let us now just, I want to give you the difference between the domains. So here the frequency is content in this signal, so it can be something like that, for example. Okay, and now let us talk about another domain, is amplitude domain. What I mean by amplitude domain, okay, amplitude domain is how the signal will be varying in the amplitude, the percentage of amplitude. So if I take strips here, maybe I can find some. Okay, anyhow. So, and we have another strip. Okay, let me do them as a lines like this. And this way, the same. Okay, and maybe this is the last term, and maybe we have here the last one. Um, Now, for the whole time of this signal, I look to this part. For example, from let's say from -5 to -4. And I didn't find in this part from -5 to -4, we cannot find any part of the signal. So the part of the signal here is 0. We don't have anything in this part. So the probability or the percentage of having signal from -4, from -5 up to -4 is equal to 0. The signal is not there. Okay. And now from -4 to -3 in this part, we found only let's say 2% of the signal. And from -3 to -2, assume that we find 5% of the signal. And from -2 to -1, let's say that you find 10% of the signal, and so on. Okay. So what that means? If I let me here, if I draw another two-dimensional signal, and I put here the amplitude, the changes in the amplitude. And then here I put the percentage of the signal in that amplitude. Okay. So the amplitude here, as we show that as we divided them this way. So maybe from 0 volt to, let's say, 1, 0.5, 1, 1.5, 2, and so on. From 0 to 0.5, we found, like, let's say 40% of the signal is there. And then in this way, and also in that way. So from 0 to 0.5, we found, sorry, from 0 to 0.5, let's say 5% of the signal. Here is 20%, here is like, and so on. What this strip mean? This strip means that what is the percentage of the signal in that amplitude from 0 to 0.5 volt? From 0.5 to 1, what was the percentage? From 1 to 1.5, what was the percentage? This kind of picture is called amplitude domain. It is hard to find such definition in books. It is not used. It is not like the title is not that famous in mathematics and probability amplitude domain. But actually, it is exactly the same concept of probability density function. The same concept of probability density function is the percentage content of any signal in that amplitude. So here we have V with the percentage. Here in the signal here, we have V with time. Here we have the amplitude with frequency. Here we have the amplitude with the percentage. So that this amplitude domain representation of any signal is nothing but the main concept behind the probability density function. So the probability density function is that in the same way. Okay. So this is the probability density function is defined in this course. We define the probability density function as f of x. Okay, so the probability that x belongs to any set B is the integration or the area under that set B of f of x dx. Okay, so the probability density function is always positive because it represents probability, so it cannot be negative. It is not possible to define the percentage to be negative percentage. The percentage is always positive. You have 0%, you have 1%, you have 2%, 5%, but cannot be negative. Okay, so it is the same. So the amplitude domain must be always positive. So f of x is greater than or equal to 0 for all x. And also the total integration of f of x must be 1. And also this fit with the concept of amplitude domain, because this is the percentage, 1%, 2%, 5%, 9%, but the total should be 100%. Okay, so this is the same concept here. So the integration of f of x dx, it must be equal to 1. Okay, and we can also define the cumulative distribution function, CDF. It is also important. The CDF is defined as the probability that this random variable to be less than or equal to certain value a small here. And this is defined as capital F of a equal to the probability that x to be less than or equal to a. And this will be the integration of from minus infinity up to a fx of x. And the CDF is always non-decreasing function. So for any b greater than or equal to a, then f of b is always greater than or equal to f of a, because b is greater than a, and this is the probability that x to be less than or equal to b must be also less than or equal to a, because b is greater than a. Okay. The same concept of for discrete probability, as we mentioned before, it can be applied for the also discrete. But in discrete case, we don't call them probability density function. We call them a probability mass function, where the summation of probability of xi in the discrete case equal to 1. And also we can define the CDF in the discrete case in this way. So f of a is the probability that to x to be less than or equal to a, and this equal to the summation from xi to be less than or equal to a, b of x of I. Okay. I will now give some example about, before we go to these distributions, I give some examples for the CDF in case of discrete case and also in continuous case. I think it is better to go to the whiteboard again, even it is not that straightforward tool, but better than writing on the PDF. Right. Okay, I hope now it is already there. So let us take one example about throwing this, for example, dice. Okay, throwing the dice, the probability or the sample space equal to, as we know, 1, 2, 3, 4, 5, and 6. Those represent the numbers, the number of dots. 1 means the number of dots. Let us assume that we define random variable x is the number of dots. So appeared or head up. So now we have x equal to 1 or 2 or 3 or 4 or 5 and 6. Okay, so the probability that x equal to 1 actually is equal to 1 over 6. And this will be the same as probability that x equal to 2 is also 1 over 6. Okay, now we can define f of a as the CDF. So this is the mass function. Now the probability mass function that we have, this is x. We have at x equal to 0, the probability is equal to 0. At x equal to 1, the probability is 1 over 6, 2, 1 over 6, 3, and 4, and 5, and 6. Okay? This is called the probability mass function. The cumulative distribution function, the CDF, is the f of a is equal to the probability that x to be less than or equal to a. Okay, let us draw now the CDF in this case. So the CDF in this case, this is for A, and this is F of A. Okay, up to 1, what is the probability that X to be, here we have A equal to 1, A equal to 2, 3, 4, 5, and 6. So we have 0 until 1. What is the probability that X less than or equal to 1 is equal to 1 over 6? So it will be just here. We up to 1 over 6. And this one, what is the probability that X less than or equal to 1.5? We don't have 1.5 because 1.5, the probability is equal to 0. We have only 1 and 2. It means that less than 1.5 is the same as 1. So the probability will be continuous at 1 over 6 until we reach to 2. When we reach to 2, the probability to be less than or equal to 2 is equal to 1 over 6 for 2 and plus 1 over 6 for 1. The total will be 2 over 6. So it will jump like this one. And it will continue. Here will be 2 over 6 or 1 over 3. It will continue until 3. Probability to be less than or equal to 3, it means that 3 and 2 and 1. And the total will be over 1 over 6 plus 1 over 6 plus 1 over 6. So we go another 1 over 6 and this way until in the same way at 5. Okay. For some reason, this stop writing. Yes. And like this one until we reach to 1. So it will be at 1, at 2, at 3. Every time I increase 1 over 6, and the last one will be 1. So it is a general rule that f of a, the limit when a goes to infinity, is always equal to 1 for any distribution. For any distribution. This one will continue. For example, what is the probability that when you throw a die, what is the probability that x to be less than or equal to 100? Of course, it will be 1 because 6 less than or equal to 100. So f of infinity equal to 1. And also f of minus infinity is always equal to 0. Okay? And the CDF is always increasing function, or at least non-decreasing function, So it will not be decreased at all. It is always start from 0 and goes up to 1. Okay, so this is the concept of CDF in the continuous, in the discrete case. In the continuous case, it will be similar. For example, if we assume that we have certain distribution function, probability density function, that it has continuous distribution, uniform distribution, like from minus 2 volt up to 2 volt. And this is for voltage V, and this is the distribution of V, FV of V. We will come to this later, actually, in more details when we talk about different distribution function in the probability. But let us take this as simple example. So in this probability density function representing the uncertainty in certain random voltage. We have certain random voltage, and this random voltage is random in some way. So it is random somehow. But even it is random, but from this description of probability density function, I can know that it is not possible to be less than minus 2. And it is not possible to be plus than minus 2. So, or plus 2. So here, minimum is minus 2, and the maximum will be plus 2. And I can compute the probability for the voltage at any value. For example, if I want to compute the probability that you will have this voltage of from, let's say, 1.6 up to 1.8, you can easily compute it because this will be the area under this curve. And also I can calculate what is the maximum here because I know the total area must be 1, and here the width is 4, so that this will be 1 over 4. because the area here will be the area of a square, and the area of the square is the length. This it will be 4, and the height will be 1 over 4. So the total area equal to 1, because I know that the total area of V of V, f of V, from minus infinity to infinity must be 1. dV, of course, must be 1. So this means that the amplitude here is equal to 1 over 4. If I want to draw the CDF of this probability density function, so I know that it should be something like that. Actually, I can mathematically compute it easily, because this will be the f of A equal to the integration from minus infinity up to A f of V dV. F of V is the probability density function. F of V actually is defined from -2, because less than -2 will be 0. Then I and from -2 up to 2, it will be 1 over 4. Then I can define it from this one. The minimum is -2. The maximum, that is A, because I'm looking to compute the probability to be the probability that X to be less than or equal to A. So from -2 up to A. Okay, this will be 1 over 4. 1 over 4 is constant. I can take it out from the integration, and this will have V d. Sorry, I have 1 here. 1 dV. Okay, so 1 dV actually is equal to V. So the result will be V over 4, and the integration is from -2 up to A. Okay, so taking this integration, substitute at A, it will be A over 4 minus, this will be -2, -2 over 4, it will be half. Okay, so half here, it will be minus will be plus half. It will be A over 4 plus half. Okay, so now if I put A equal to -2, because A here, the minimum that you can take A will be -2. So -2 divided by 4 equal to minus half plus half equal to 0. So here at -2, so it will be here at -2, f of A, it will start 0. Okay, because here we have A. And then at A equal to 0, this will be 0 divided by 4 is 0 plus half. The result will be half. So at 0, it will be half. This one. Okay. What is the maximum of A? The maximum of A is 2. At 2, it will be 1. So this is at 2. The result will be here 1. So actually, it will be this form. Sorry that it will not coming to the points that I bought, but I will do it here. So this is the points here that we have. So now, and after 2, it will be always 1. So, and this here, we will have 1, and starting from 0 at -2, and 1 at 2, and it will continue 1, and behind -2 will be 0. So this is the CDF, the cumulative distribution function, the CDF of this uniform distribution. This is called uniform distribution. This is one of the simplest distributions applied in probability theory. Okay, so this is the way that how we can build the CDF. We will come to more details about the distribution, because we will talk about different kind of distributions later, like Gaussian distribution, Laplacian distribution, Poisson distribution, delta distribution. We'll see different kind of distributions when later on in this course. But this is one of the simplest distributions in the continuous case. Okay. So this was already explained now, and we start with some distributions in the discrete case before we go to the continuous case. The simplest distribution. What is the simplest uncertainty? The simplest uncertainty is the uncertainty which has two outcomes. when we have any uncertainty with only two outcomes, success or fail, then we have the simplest one because we have uncertainty. There is no uncertainty with single outcome. If we have experiment gives us single outcome, it doesn't have uncertainty. We cannot apply probability. But if we have the minimum set or the sample space, the minimum content of the sample space must be at least two outcomes. And in these two outcomes, we cannot decide which outcome will come next. So now we have uncertainty. So this is the simplest random variable. It's called Bernoulli random variable. In the Bernoulli random variable, that it is a random variable, it has only two outcomes, and these outcomes we call them success x equal to 1 and failure x equal to 0. You can define a different way. You can say that I want to define it x equal to 1 for success and x equal to -1 for failure. But in that case, you cannot define this as Bernoulli. Bernoulli defined as with these numbers: x equal to 0 for failure and x equal to 1 for success. Okay, but in general, of course, you can put any numbers for those two outcomes. Distinct numbers, of course. Then the probability that x equal to 1 equal to b, because it has only two outcomes. Then the other one will be 1 minus b, because the summation must be 1. The summation must be 1 as far as one of the outcomes must be or must appear. So in this case, you have one of them. Okay. After the simplest Bernoulli distribution, then we have the binomial random variable. Binomial random variable is nothing but the summation of Bernoulli distribution. So if you repeat Bernoulli distribution several times, you will have binomial distribution. Okay, so binomial distribution is, as you can see, the summation from k equal to 1 up to n xk. Xk can be 0 or 1, every one, success or fail, success or fail. So the summation will be y. Y is called binomial distribution. Why? Because if all outcomes are 0, y will be 0. If only single one of them will be 1, y will be 1. If two of them is 1, y will be 2. If three of them are 1s, then y equal to 3, and so on. Okay, so y in this case is a random variable which takes values of 0, 1, 2, 3, up to n. It can take up to n. So it is like multi-level from 0 up to n. Sorry, from 1, not 0, from 1 up to n. Okay, 1 up to n is the k, the number of repetition. But of course, for the random variable itself, it can be 0. If the xk, all of them, they are 0, then the outcome will be 0. Okay, now let us go another time for the white screen, because there are some important things that I want to explain before I continue in the slides. You can see that I'm trying all the time to go slowly for the basic things, because we try to build the concepts to be very clear for you. After that, we can speed up. But in the beginning, we try to put things like carefully and slowly, and be sure that you understand those basic things. Okay. Stop sharing. Share the whiteboard again. Okay. I like to start with some simple examples. So as we said that here, y is a random variable consisting of different, like, Bernoulli distribution, that it will be, for example, x1 plus x2 plus x3 plus x4 until plus xn. If we repeat Bernoulli distribution n times. Okay, then as I said, if all of them are 0, then y equal to 0. In case x1 equal to 0, x2 equal to 0, until xn equal to 0. And then y equal to 1 if any of those x, one of them equal to 1 and the other 0. And we can continue until y equal to n, and at x1 equal to 1, x2 equal to 1, until xn equal to 1. If all of them equal to 1, it will be 1 plus 1 plus 1 plus 1 n times, so it will be n. So y equal to n. So y takes values from 0 up to n. What is our duty now? Our duty now is to find the probability of each case. What is the probability that y equal to 0? What is the probability that y equal to 1? Up to what is the probability that y equal to n? Let me start with the simplest cases. We know that, as we said, that x equal to 1 with the probability b, and x equal to 0 with the probability 1 minus b. Okay? This is for single Bernoulli random variable. So you will get x equal to 1 with b and x equal to 0 with 1 minus b. And here we assumed that the repetition of the experiment are independent. So x2 to be success or fail, okay, does not depend on x1 if it was success or fail. And x3 to be success or fail is not depending on x1 and x2, and so on. So every experiment is repeated independently. So in this case, or in this case, this Bernoulli distribution defined. Okay, so keep in mind that binomial distribution is defined for independent occurrence of the experiment, of Bernoulli experiment. Okay, what is the probability that y equal to 0? This one is easy, actually. This one is easy because y equal to 0, it means that x1 equal to 0 and x2 equal to 0 and x3 equal to 0 and x4 equal to 0 until xn equal to 0. So every time we will have this 1 minus b, as you can see it here. So every time we will have 1 minus b. So in this case, the probability, I can write it easily, that probability y equal to 0 is equal to 1 minus b times 1 minus b times 1 minus b n times. So simply it will be 1 minus b of the power of n. This is the case that y equal to 0. Also, this one is easy, the last one. The probability that y equal to n, it means that x1 equal to 1, x2 equal to 1, x3 equal to 1, until xn equal to 1. And this to happen, it means that everyone, the probability of everyone is b. So it will be b times p times p until n times. So it will be p of the power of n. So these two cases actually easy to find. But in the middle, we need to think a little bit more. To explain what is going on in the middle, let me take a simple, very simple example with the 3 cases to see what is going on. I think maybe I am not a fan for football, but at least I know some figures like Muhammad Salah and Messi. I hear about them, but I'm not that fan of football in general. But assume that we take, like, you heard about a game played, like a team where, for example, Messi is playing, and you heard that the team of Messi score or win like 1-0. Okay, so uh, the probability that if the probability based on the history that Messi is scoring in each game, the probability it was, let's say, 0.2, means that 20% that Messi will like score in each game. So you know the probability of P. Okay, so if that team win 1-0, then what is the probability that Messi scored that goal? It will be 0.2. That's all. Okay. Now assume that that team win 3 they play 3 goals, or they score 3 goals, 3-0 or 3-1. We don't care about the other one. But now look about this three. What is the probability that Messi has scored all 3 goals? It will be P times P times P. So it will be 0.2 of the power 3. What is the probability that Messi didn't score any of those? It will be 0.8 of the power 3. This is what we explained already here in this one and also in this one. The tricky point, if I asked you, what is the probability that Messi scored only 1 goal? Okay, so in that case, you can say that, okay, probability that he scored 1 goal, it will be 0.2. That is true. 0.2 P. This will be of the power 1 because he scored only 1 goal. And other 2 goals was scored by someone else. So it will be 1 minus P of the power of 2. And uh, this intuitive thinking is correct. Okay. But it comes another question now. Which goal he has scored? For example, because they were 3 goals, so it can be like Messi score the first one, but the second one and the third one another player. Or it can be the first one another player and he scored only the second and then another player. Or he can score only the third goal, so it will be none, and then Messi. So actually we have 3 possible cases. So it can be this one or this one or this one. Since it is or, and we know that from previous lectures that or means that we add because they are mutually exclusive. If he scored the first one, he will never be able to score the second one because he scored only 1 goal in this case. So in this case, we multiply 3 times this P, 1 minus P of the power square. Okay. So we need to define this number in general way. Of course, now in the 3 cases is easy. So if now what is the probability that 2 goals has been scored by Messi? 2 goals, not 1 goal. 2 goals. Okay. So in this case, I hope this will happen without problems. So I will take off these and go back to the pen. So this is the probability that y equal to 1. 1 out of 3. Okay. 1 out of 3. What is the probability that Messi scored 2 goals? It is easy to say that since he scored 2 goals, the probability of scoring is B. So it will be B squared because he did 2 goals. So B times B. And the third goal was done by someone else. So it will be 1 minus B. Okay. But what's the number that we put here? So we can do the same way. So Messi, he scored 2 goals. So it will be M someone else. Or it can be M someone else M. Or it can be someone else M. We don't have other options. So we have only 3. So this one always also to be 3. Okay. And finally, probability that y equal to 3, as we said that it will be only one case, that will be M. And in this case will be P of the power 3, as we said. And probability that y equal to 0 will be 1 minus P of the power of 3. So here we have all cases that it described. Okay. So for 3 cases is easy. But actually, if you generalize this, for example, what about 5 cases? What is the probability that Messi scored 1 goal from 5 goals? Or what is the probability that he scored 2 out of 5? So it will be like long story in this case because you need to say that 2 out of 5. So we have 5 goals, like 1, 2, 3, 4, 5. Then it can be he scored the first one, but not the second, not the third, not the fourth, but the fifth one, or the first one, the second one, not this one, not this one, not this one. And you can continue with this calculation. Of course, no one is interested to go with this calculation, especially for large numbers. Okay. Because of that, we have some symbol representation, mathematical, it is called, this is the name binomial come, binomial representation of mathematical binomial distribution for this one. And in general, if the probability of having y equal to k, okay, out of n trials, it is given in this way. It will be in this case calculated as n factorial divided by k factorial multiplied by n minus k factorial multiplied, because y equal to k, k success, it will be p of the power k, x equal to 1, times the rest is 1 minus k. 1 minus k will be n minus k. So this is the general formula of the binomial distribution. N factorial divided by k factorial times n minus k factorial. You know what is the meaning of k factorial? For example, n factorial means that n times n minus 1 times n minus 2 and so on until 1. So for example, 4 factorial will be 4 times 3 times 2 times 1, and this will be 4 times 3 is 11 or 12 times 2 is 24. Okay, and also factorial has special property that 0 factorial equal to 1. Okay, 0 factorial equal to 1, and you can calculate in this way. For example, if as I said that the match ended with 5 goals, and we like to compute what is the probability that Messi scored 2 goals out of 5, and as I said that the probability that of scoring 1 goal is 0.2. Okay, in this case, it is very easy to calculate what is the probability that he scored 2 goals out of 5. It will be 5 factorial divided by 2 factorial. 5 minus 2 is 3 factorial. And then b is equal to 0.2. It will be here 0.2 of the power of 2 times 0.8 of the power of the rest. It will be 3. Okay, of course, 5 factorial, to calculate this one, you can make this 5 factorial is 5 times 4 times 3 factorial times 2 factorial is equal to 2 times 3 factorial times 0.2 of the power 2 times 0.8 of the power 3, and the 3 factorial cancel 3 factorial, 2 cancel 4, it will be 2, it will be 10. 10 times 0.2 square times 0.8 of the power of 3. Then you can calculate what is the probability of having this percentage. So this is the way to calculate the binomial distribution. And also about the previous example that I gave before the break, that if you would repeat the experiment until you get head, for example, and the probability of getting head is equal to b, and the probability of get tail, for example, it will be 1 minus b, and we said that the probability and our random variable is defined as the number of flipping. So the probability that you have I flipping to get b, this will be, as we mentioned, this will be that b times 1 minus b of the power I minus 1, or n minus 1 if you define it as n, because before you get b, it means that you get I minus 1 times of tails. Okay, so and one of the questions here that prove that the summation of b of I from I equal to, because I can be minimum 1, from I equal to 1 up to infinity. Okay, from I equal to this equal to 1, because the summation must be 1. The summation must be always 1. Okay, so now if you change, because at I equal to 1, this I minus 1, it will be 0. So it is the same to say that it will be the same to say summation. Of course, we can take b outside the summation because there's no I here, and I will make it based on k, and saying that k from 0 up to infinity, Okay, it will be 1 minus b of the power of k. It is the same as this one, exactly the same, because infinity minus 1 is infinity. At I equal to 1, k equal to 0, because here I put k instead of I minus 1. Okay, so you know that 1 minus b is, for b is not equal to 0, 1 minus b is fraction. So it will be like greater than 0 and less than 1. Okay, let us define 1 minus b. We call it like x. Okay, so it will be like summation from k equal to 0 to infinity, x of the power k. And here outside we have b. Okay, so this will be what? This will be x of the power 0 equal to 1. You know that any number of the power 0 equal to 1. So it will be 1 plus k of the power 1 is x of the power 1 is x. K equal to 2, it will be x squared plus x cubed plus up to infinity. Okay, yeah. So now let us call this y equal to 1 plus x squared plus x cubed plus up to infinity, as I said. So now this the same will be the same, y equal to 1 plus, if you take x as a common factor, it will be here 1 plus x squared plus x cubed up to infinity. Actually, this one is the same as y. So y equal to 1 plus x times y. And then you can say that you can take y to that other side, and then y equal to 1 divided by 1 minus x. Okay? Yeah. So in that case, what is x? We said that x equal to 1 minus p. So 1 minus 1 minus b, actually y equal to 1 divided by b. So this is y equal to 1 divided by b. And here we have b outside. So b times 1 divided by b cancel b, and the summation is 1. So this is the proof that the summation of b times 1 minus b of the power of I minus 1 from I equal to 1 to infinity is equal to 1. So this is the proof that I mentioned before the break, because I thought that it is already in the slide, but since it is not in the slide, so this is the way I put it here. And I put it, it is like simple math, but still we might need such kind of expansion and resolving of infinity series somewhere in the future in this course. Okay. Yes. Actually, the time is running now, so we are already done with time. So here you can find some examples, so please try with them. Simple example, as the example that we did in the football example. Okay, so there's another example here. Several examples that I put so you can apply this binomial distribution. It can be expanding to be multinomial distribution. Binomial that we have only two cases. The multinomial that we have several cases. Multinomial we have several cases. For example, assume that there is a survey is done, and in the survey that I will ask you about this course that you attend, and I gave you several like possibility in the survey. For example, if I give only two possibilities, that the course is good, the course is bad, only two possibility, this could be represented by using binomial. For example, if even I don't like to write over this PDF, but let us do it to save time. Okay, comment. Okay, so now in this course, you have survey. In this survey, that you can select that successful code, successful course. It means that course is good, like good, and then you select or bad course or failed course. Then I made this survey over like all my students. I have in one course here 160 students, and with you with many students, and collecting the results that I have the probability to have the course is good, let's say zero point 0.3, and the probability that the course is bad is 0.7. Okay, so in this case I have binomial distribution. So then I can calculate, for example, if I in the future I have course with 8 students, then I can compute what is the probability that 2 out of them will say that it is good, and what is the probability that 5 out of them will say that it is bad. In this case, we can use the binomial distribution. But assume now that the survey is not only that basic two choices, but we have other choices that the course is excellent, and the course is very good, the course is good, the course is bad, and the course is very bad. So now we have, actually in this case, we have 1, 2, 3, 4, 5. We have 5 options in this course. In this case, I cannot apply binomial distribution. What we need to apply? We need to apply multinomial distribution. In multinomial distribution, I will calculate how many selecting excellent. For example, assume that I did this for 1,000 students. Okay, so okay, it's a problem that. Okay, so for those who selected excellent course, they were 100 students, 200 selected very good, let's say 300 selected good, and let's say that 400 selected that it is bad, but the total is 1,000, so the number must be 1,000. So here we have 7. Okay, so here we have 700 and 300, so already 1,000 now, and maybe 0 selected very bad course. Okay, so the probability 1, probability of selecting excellent, it will be 0.1. Probability of selecting very good, it will be 0.2, and 0.3, and then 0.4. Okay, so this is now we have this distribution, and B5 equal to 0. Now we have the distribution of this case. Okay, assume now that you have another like student, okay, that he or maybe 10 students in one course, and I like to see what is the probability that 2 of them will select excellent, and 3 of them will select very good, and the rest 5 will select good, and 0 will select bad, and 0 will select very bad. I'd like to calculate this probability. To calculate this probability, I need to use the multinomial distribution. So it is calculated in this way. N factorial. Now in this we have 10 students, so it will be 10 factorial. I like to calculate what is 2 select excellent. So here will be x1 equal to 2 factorial, and 3 very good. Here will be 3 factorial, and 5 to be good will be here 5 factorial, and 0 factorial equal to 1. Then I use the probability. So the probability of 1, I know it already from history. So it will be 0.1 of the power square, 0.2 of the power 3, and 0.3 of the power 5. So in this way, we can calculate the probability of multinomial distribution. Multinomial distribution is not that much used in some application, but it is very widely used in, for example, in machine learning. We use this multinomial distribution in order to learn some distribution of the survey. When they make survey, and then they want to get some conclusion from the survey, or to get some information from the survey, we can use this multinomial distribution. Okay. What else? Here we have example, so it is almost the same example it was given. Okay, so that's all. Actually, as I said, that this should be covered in the previous lecture, but in the previous lecture we introduced the how to use Octave to compute some like probabilities and how to make some Monte Carlo simulation. We will come back to that, to the calculations using Monte Carlo from time to time. This should be like running in parallel in this course with the theoretical analysis or theoretical study. But of course, I need uh, uh, maybe this lecture and also next lecture maybe to concentrate more on the theory part in order to cover enough part to see more than about the simulation and emulation application. Anyhow, I will distribute today to you the lecture which is supposed to be the third lecture, and this will be the material of the next week, inshallah. And also, I will send the quiz to Dr. Farhat, so you can arrange with him if you want to take the quiz today, or you do prefer to practice yourself about these concepts before you come to the quiz. And then I don't have any objection the time that you perform the quiz. It should be before the next lecture. This is the important thing. But it can be today, it can be Wednesday, it can be as you arrange with Dr. Farhat, so I have no objection against that. Okay. Now I open the discussion. If you have questions, you can ask. Feel free to ask. How do you feel about the speed uh, of the like material that we give? Are we sometimes I feel that we are very slow, but I don't know if it is fine for you to go with this speed, or you like me to because the material is too much material. And when we discuss with the postgraduate program committee, Dr. Farhat, maybe he remember that. So we mentioned that two ways, that either we go with the make my main objective to cover the whole material, and in this case, I need to speed up more, but at the same time, you will receive a lot of information. We can go up to the estimation theory, and we can go maybe up to the stochastic differential equations. We can cover a lot of topics, or we can just go a little bit slowly, but to guarantee that you understand those basic things. So it is up to you. If you want me to speed up a little bit, I can do that. Okay. I will just stop recording and then we can discuss more about these things now.